What if the solar panel on your neighbor's roof actually started out as a pile of sand? Take a moment to picture that transformation. Sand, the stuff you find between your toes at the beach, somehow turning into a smooth, glassy surface capable of generating clean electricity for decades. This isn't just possible. It's what happens every day inside high-tech factories around the world. But how do we actually turn one of Earth's most humble materials into the sleek, blue rectangles that power everything from homes to satellites? Let's trace the journey of a solar panel, step by step, from raw materials to green energy powerhouse. It all starts deep underground with silica sand. This sand might seem totally ordinary, but its hidden power emerges through the magic of chemistry and precision engineering. Pure silicon is what we're after, because it's the cornerstone of most commercial solar panels, specifically crystalline silicon models, which dominate the market today. So, how do you extract pure silicon from ordinary sand? The sand is heated to temperatures above 1,800 degrees Celsius in massive furnaces, where it reacts with carbon to release the oxygen and leave behind silicon. The result is called metallurgical-grade silicon, still packed with tiny impurities that would ruin a solar panel's performance if left untreated. That means a second purification step is needed. The silicon is reacted with gases like hydrogen chloride at high temperatures, forming trichlorosilane gas, which can be precisely separated from impurities. Then, this gas is decomposed back into hyperpure polysilicon through a process that's almost like industrial-scale crystal gardening. Giant rods of silicon slowly grow, frosted with a layer of pure silicon atoms. When finished, these rods can be sliced and shaped with a purity that can exceed 99.999%. When you hold a solar panel and see that flat, shining surface, you're really seeing hundreds of thin wafers, each just fractions of a millimeter thick, all created from those silicon rods. Making these wafers is a precise art. The rods, often referred to as Boules, are carefully sliced into ultra-thin discs using diamond wire saws. Each wafer starts out looking a lot like a clear, fragile coin. But at this point, they're still just silicon, not yet capable of making electricity. Now for the secret ingredient: sunlight. Silicon can convert sunlight into electricity thanks to a quantum property called the photovoltaic effect. But first, the wafers must be specially treated so that they can separate charges when they're hit by photons. This treatment involves adding microscopic amounts of other elements, like phosphorus or boron, to create what's known as a P-N Junction. Imagine the wafer as a layered sandwich, where one layer is hungry for electrons and the other layer has a few extra electrons ready to be shared. When sunlight zaps the sandwich, the energy knocks electrons loose, and the different sides of the stack naturally usher those electrons toward metal contacts, generating usable electric current. But the story doesn't end there. The silicon wafers are still vulnerable to the world. On their own, they're fragile and reflective. If you put a raw silicon wafer in the sun, it would bounce away most of the light, wasting precious energy. To fix this, manufacturers coat the surface in a thin layer, often titanium dioxide or silicon nitride, that acts as an anti-reflective shield. Now, more sunlight is absorbed instead of reflected, and the panel's efficiency jumps dramatically. If you've ever noticed that deep blue, almost purple shimmer on a solar panel, that's the anti-reflective coating at work. Next, ultra-fine metallic lines, usually made of silver or aluminum, are printed across the wafer's surface. These act like microscopic wires, grabbing the freed electrons and providing a direct route for the current to flow. These lines have to be ridiculously thin to avoid blocking the sunlight underneath, but thick enough to carry the electrical load. Achieving this balance is one of the quiet miracles of industrial design that makes solar power possible and affordable. Once printed, the wafers are baked in industrial ovens at carefully controlled temperatures to fuse the contacts, strengthen the junctions, and harden the anti-reflective coat. Each fragile piece is tested, sorted, and individually measured for performance. Only the best wafers make it to the next stage. Now, the individual cells are ready to join forces. On their own, a single cell only produces about half a volt, enough to power a tiny LED. But when dozens of cells are wired together in a matrix, their voltage adds up, forming what's known as a solar module or panel. Technicians meticulously assemble cells into precise arrangements, soldering the metallic backings so the current flows seamlessly from cell to cell. But a solar panel has to stand up to decades of sun, rain, hail, and even a child's stray soccer ball. That's why the most delicate bits are sealed beneath multiple barriers. The cells are sandwiched in layers of clear, flexible polymer, often a type of plastic called EVA, which cushions and seals them. This sandwich is then topped with a toughened sheet of low-iron glass on the front and a weatherproof backing on the rear. The whole assembly is pressed together in a giant laminator, a kind of industrial panini press under heat and vacuum, so air bubbles can't sneak inside. Once everything cools down, the solid rectangle that emerges is almost ready for the outside world. But not quite. Sturdy aluminum frames are added to the edges, making it safe for installers to lift and mount the panel on roofs or in solar farms. Waterproof junction boxes are attached to route the electrical output, and care is taken to ensure safety and resistance to corrosion. Every panel is tested again, flashed with powerful simulated sunlight to verify output, stability, and durability. Only then does it earn the right to leave the factory and start producing green energy wherever it's installed. Reflect on that for a moment. A solar panel isn't just a simple sheet of glass. It's a marvel of chemistry, physics, material science, and patient craftsmanship. Each step, from purifying sand to layering delicate films and assembling complex electrical networks, is the product of decades of innovation. It's a testament to what humans can accomplish when we chase efficiency and sustainability at the same time. But why does this process matter on a global scale? For one, every solar panel that's manufactured and installed means less reliance on fossil fuels, less coal, less gas, less oil burned just to turn on your lights. Solar panels offer a way to capture energy directly from our nearest star, transforming it into clean power with no moving parts, no fuel, and no emissions once installed. The story of sand turning into solar energy is also a story of how we can take nature's raw resources and reshape them to benefit generations. There's still so much room for improvement, too. Scientists are continuously finding ways to make cells thinner, panels lighter, and processes cleaner. Imagine a world where solar panels are printed like newspapers or woven into window glass. The latest experimental techniques are pushing the boundaries, using different materials like perovskites, organic blends, and quantum dots to achieve even higher efficiencies or lower manufacturing costs. Still, crystalline silicon solar cells dominate for now, partly because the method for making them, as you just heard, is tried, tested, and has benefited from tremendous economies of scale. Gigafactories around the world churn out millions of panels each year, with improving recycling techniques on the horizon to recover precious materials and reduce waste. So next time you see a rooftop glinting in the sun, or pass by a vast solar farm blanketing a hillside, remember the journey. From humble sand, purified in blazing furnaces, crafted into intricate microstructures, protected by glass, and finally set out to harvest light from the sky. It's a quiet revolution, and it's already transforming how we power our lives, one panel at a time. In the end, the lesson of the solar panel is about more than just electricity. It's a reminder of how simple elements, sand, sunlight, ingenuity, can be combined through science and hard work to change the world. And maybe, just maybe, the future of green energy begins with noticing the extraordinary potential lurking in the most ordinary things. Overshri, ma, of the Bachamar, bo, wan, bo,